Hey everyone. In this lesson, we're going to start chapter 4, linear correlation and regression analysis. And we're going to cover 4.1, which is an intro, and then 4.2, which is going to introduce the scatter diagram. So as far as the introduction goes, not much. Really, the main idea is that this chapter is going to cover two things, correlation and then regression. So we're going to start with correlation. And correlation is a technique that measures the strength of the relationship between two variables. So now we're going to have paired data. So we're going to have two variables and they're going to come in pairs. So we're going to have a set of ordered pairs, and we're going to be interested to see if there's a linear relationship between the two variables. If we determine that there is a correlation, specifically a linear correlation between the two variables, then we would perform a regression analysis. Whoops, let me get my highlighter. So we would perform a regression analysis, which is just a statistical technique that's going to produce a model of the relationship between the two variables. And we'll do that later on in this chapter. So really what I want to do in this lesson is let's talk about scatter diagrams. And some of you are familiar with scatter diagrams. So a scatter diagram is just a graph that represents the ordered pairs of data on a set of axes. So if we have a set of ordered pairs and we plot them, we have a scatter diagram. And just to kind of look ahead, in the first example that we're going to do, I have you looking at 5 different scatter diagrams. So this is what a typical scatter diagram, looks like. We have the X and the Y axes, and we have our ordered pairs. So we'll get to example 1 in a minute. First, I want to talk about the different types of linear correlation. So the key word in this chapter is linear. Specifically, we're interested in a linear correlation. Linear having the word line in it, right? So if we plot our ordered pairs and we see that there seems to be some sort of line relationship that's apparent, then we're going to say that the two variables have a linear correlation. But there's two types of linear correlations. We have a positive correlation or a negative correlation. So let's start with the positive correlation first. So there exists a positive correlation between two variables, x and y, if high measurements for the x variable tend to be associated with high measurements for the y variable, and low measurements for the x variable tend to be associated with low measurements for the y variable. So I think it's nice to take this statement in words and let's put it into a picture. So what is this really saying? So what it's saying is if I have paired data, X and Y, and I plot the ordered pairs, and I see some sort of positive or increasing relationship, then we say there's a positive correlation. So you see what's happening here? As the X values are increasing, so are the Y values. And I can imagine drawing a line through my data, right? And the line is increasing. So this would be an example of a positive correlation. Now, if I had the opposite relationship, so let's look at this next definition, a negative correlation. So if there was a negative correlation between two variables, x and y, that would happen when high measurements for the x variable tend to be paired with low measurements for the y variable. And then low measurements for the x variable tend to be paired with high measurements for the y variable. So let me give you an example of what that may look like. So if I have my x and my y axes, let's suppose my scatter plot looks something like this. I definitely see a pattern here, right? These points don't form a perfectly straight line, but you can imagine fitting a line through this data set, right? You can imagine fitting a line through those ordered pairs or as close to as many of them as we can get. And that line is negative or has a negative slope or it's decreasing, right? So what this means is that higher values of y tend to be paired with lower values of x, and lower values, or I'm sorry, higher values of x tend to be paired with lower values of y. So we have that negative relationship. So this would be an example of a negative correlation. But not all paired data has a positive or a negative correlation. It's very possible that there's no linear correlation between our data. So that's this third definition here, no linear correlation. So that means that there's no linear relationship between the two variables. And we don't see any predictable straight line pattern. So I'll give you an example. So if we had something like this. So you see this scatter plot here. These points are kind of scattered all over the place, right? We don't see any distinct line pattern. I can't imagine fitting a positive or a negative line through here, right? There seems to be no linear correlation. But the points don't have to be scattered all over the place. You can have something like this too, where there's no linear correlation. So maybe I have something that looks like this. So in this example, there definitely seems to be some sort of relationship between X and Y. It's just not a linear relationship, right? You can't fit a line, right, through this paired data. A line wouldn't be appropriate here. There's definitely some sort of relationship, maybe like a curved linear relationship, but there's definitely not a linear relationship. So this would be another example where our scatter plot suggests that there's no linear correlation. So what I want to do right now is let's go to the first example and let's practice identifying whether there's a positive, negative, or no linear correlation between the two variables. So we're looking at example 1. So let's look at plot A. I definitely see a pattern, right? There seems to be a correlation between X and Y, and I can imagine fitting a line through my data and a line that's decreasing, right? That's negative. So there seems to be a negative linear correlation between X and Y in the first graph. Now, if we look at the second graph, graph B, again, I do see a line pattern. And if I were to fit my line through this data, the line would be increasing or positive, right? So as X increases, Y is also increasing. So I would definitely say there seems to be a positive linear relationship between the two variables in graph B. Graph C, again, I do see a linear relationship. If I were to try to fit a line through this data set, the line would be decreasing, right? So higher values of Y tend to be paired with lower values of X, and higher values of X tend to be paired with lower values of Y. So I have this negative relationship. So graph C would be an example of a negative linear correlation. And then graph D, there definitely seems to be some sort of relationship between X and Y. It's just not a line, right, or a linear relationship. So D would be an example of no linear correlation. And then let's look at the last one. Let's look at graph E. E is very similar to D. There doesn't seem to be a linear correlation, right? I don't see a line pattern here. The points are really spread out from one another. They don't look like they're going in the positive or the negative direction. So again, in this instance, I would say that there's no linear correlation. So example 1 is just a nice example where we have to practice identifying positive versus negative versus no linear correlation. So hopefully now you're able to see the difference. Now, before we get to example 2, I want to talk about strength for a minute because we are going to talk about this in the next lecture, but I kind of want to start the ball rolling on that conversation. So I'm in the whiteboard right now because I just want to give you an example. So let's look at graph A. We have my variables X and Y, and they're going to have a positive linear relationship, as you can see here. So if I were to draw a line through this, it would look something like that, right? Versus, let me give you another relationship between X and Y in graph B. It's also going to be positive but I want you to tell me the difference. So look, in graph B, there's definitely also a positive linear relationship, right? I could definitely imagine fitting a line pattern through those ordered pairs. So my question to you is, in which graph does X and Y have a stronger relationship? So I want you to think about it for a minute. If you had to answer my question, which relationship, the relationship in graph A or graph B, do you think is stronger? And the answer is the relationship, they're both positive, right? So let's just make a note that these are both positive relationships, but the relationship in graph B is going to be stronger. And the reason is these ordered pairs or these points on this graph tend to cluster more closely around that line pattern, right? Whereas in graph A, the points still are increasing, right? As X increases, Y increases, but the points are more spread out. So they're more loosely around that straight line that we imagine fitting through that data set, right? So the closer the points are to that straight line, the stronger the relationship. So I'm writing that down. So the closer the points are to a straight line pattern, the stronger the correlation. So with that being said, the relationship between X and Y in graph B is stronger because we definitely see that more definitive line pattern, right? The points in graph B cluster more closely around that imaginary line. And we're going to talk a lot more about the strength of these positive and negative linear correlations, but I did want to point that out. So let's go back to the worksheet and we'll do example 2 and then we'll wrap up this lesson. So in example 2, I said for each of the two variables, state whether you would expect a positive, negative, or no linear correlation. So now we're kind of putting these in the context of something, right? In the ones that we were practicing above, X and Y weren't named. I didn't have units or specific variables, right? I was just saying, okay, here's variable X, here's variable Y, this is what their relationship looks like. But now I'm taking the picture away and I'm saying, okay, let's suppose we have these two variables. Would you expect a positive, negative, or no linear correlation? So let's look at A. A says the number of hours practicing bowling and bowling score. So let's think of the number of hours practicing bowling. That's going to be X. And your bowling score will be considered Y. And the reason for that is typically we let X be the independent variable and we let Y be the dependent variable. So I'll write this down on the whiteboard and then we'll pick up. So typically in math, X is the independent variable and we usually let Y be the dependent variable. So then the question becomes, how do you know which is which? Which variable should be X, which variable should be Y? Well, this is what I usually do. Because just think about it this way. The dependent variable depends on the values of the independent variable. So the values of y are going to be influenced by x, in other words, and x doesn't get affected by y's values because it's independent. So like, let's go back to this example, part A. What's going to depend on what? Is the number of hours that you practice bowling going to depend on your bowling score, or is your bowling score going to depend on the number of hours that you practice bowling? And that's the way it's going to be, right? Your score is going to depend on how much you practice. So y is going to be the dependent variable. So now, do you expect there's going to be a positive or negative relationship? There's definitely going to be a relationship between how many hours you practice and what your score is going to be, right? So I like to just use arrows. Let's say X was increasing, right? So as the number of hours that we practice goes up, what's going to happen? We're going to get better at bowling, and then what's going to happen to our score? Our score is also going to go up. So what type of relationship is this, right? So as X is increasing and Y is increasing, that's going to be a positive correlation. So we would expect there's going to be a positive correlation between the number of hours that you practice bowling and your bowling score. So let's look at part B, the number of hours that you practice golf and your golf score. So the number of hours that you practice golf, that's going to be X, and then your golf score is going to depend on how much you practice, right? So that's going to be the dependent variable. Now, we went through this a couple of lessons ago. Remember, we had that example with Brett, the baseball player, and Woods, the golfer. And I told you guys that when we play golf, you want to have a lower score. The lower the score, the better. So let's think about what happens. The more we practice, so as the number of hours that we practice increases, we're going to get better at golf. So then what should happen to our score? The score is also going to get better, right? But in golf, the lower the score, the better. So it should go down. So what type of relationship is this? So as X is increasing, but Y is decreasing, now we have that opposite, right? Or that negative relationship. So we would expect a negative relationship between the number of hours that we practice golf and golf score. What about C, temperature outside and ice cream sales? So temperature outside is going to be X, that's the independent variable, and ice cream sales is going to be Y, because the amount of ice cream that's sold is going to a lot of times depend on the temperature, right? So what happens? As temperature increases, what's going to happen to sales, right? So as the temperature goes up, the hotter it gets outside, more people tend to buy ice cream, right? Think about the summertime. So the sales are going to increase, right? You could think about it the other way too. What happens as temperature goes down? When it's cold, the ice cream sales are going to go down as well, right? So higher values for temperature tend to be paired with higher ice cream sales. Lower temperatures are going to be paired with lower ice cream sales. So this is going to be a positive relationship. I also like to take this opportunity to point out that correlation doesn't necessarily mean causation. So in other words, is the temperature outside the only thing that's going to cause ice cream sales to change, right? And maybe I'll give you another example too. Would you think that there's a correlation between ice cream sales and the number of drowning deaths? And a lot of people would say no, but there does seem to be a correlation between ice cream sales and drowning deaths, because ice cream sales are usually high when it's hot outside, and when do drownings mostly occur? In the warmer weather, right? But that doesn't mean that ice cream sales cause drowning, right? Even though there's a positive relationship, the reason is that there's that underlying factor or variable, right, which is temperature outside. So I don't want you to necessarily interpret it as the change in one causes the change in the other. That's different than having a correlation. So I like to point that out. So let's look at D. So it says the amount of alcohol that you consume and your reaction time. So your reaction time is definitely going to depend on how much alcohol you have, right? So let's imagine what's going to happen as the alcohol goes up. The more alcohol you consume, what's going to happen? It's gonna your reaction time, and what I mean your reaction time is your reaction time to your environment, like to catch a ball if I throw a ball at you, to recite the alphabet, to walk on a straight line from point A to point B. So how you react, the more alcohol you have. So the more alcohol you have, the longer it's going to take you to react, right? Your reaction time gets higher because it's going to take you longer. So the more alcohol you consume, the longer your reaction time. So that's going to be a positive relationship. Pardee says, what about a mother's birth weight and her child's birth weight? There doesn't really seem to be any correlation between a mom's birth weight and her child's birth weight. So this is going to be an example of no linear correlation. Part F, what about the amount of grams of fat that you consume daily and your cholesterol level? So your cholesterol is usually affected by the amount of fat that you consume. So your cholesterol level is going to depend on the amount of fat. So X is going to be the fat you consume, Y is going to be your cholesterol level. So let's think about this. As the amount of fat in your diet goes up, your cholesterol is probably going to go up too, right? So that's going to be a positive linear correlation. And then we have one more G, a person's weight and the value of their home. Probably no linear correlation, right? I don't think it would make sense to have a correlation between somebody's weight and the value of their home. So we're going to stop here. In the next lesson, we'll start section 4.3 and we'll talk about the coefficient of linear correlation.